Did you say you were happy with this microphone, or you want to take this?
That should work fine for me.
Okay, right. Okay, so. Presentation here too. Okay, so our next presenter is Owen O'Donnell from VIAVI. Am I getting this correctly? VIAVI? VIAVI. Because I spoke with few VIAVI people, and even them, they used to do different versions.
We'll take either one, especially if you're placing an order. Okay, so good afternoon, everyone, and thank you very much for the invite to be here. This is it's a great opportunity to speak to learned people. My name is Owen O'Donnell, and I'm a product marketing manager for VIAVI. Now, VIAVI, we're a test and measurement company, and we're actually very close. We work in Dunleary, which is only 6 kilometers that way. So I probably had the easiest commute of all the presenters today. So today I'm going to talk about post-quantum cryptography and the reason it needs to be tested, but at scale, which is really important. And hopefully, after seeing this presentation, you'll understand why. So let me begin by just setting a couple of terminology pieces to kind of begin with. So quantum computing is, I guess most people are aware, they're on their way. So, we're going to have quantum computers very soon. It could be 2030, it could be maybe a couple of years after that. And while they will bring, huge amounts of benefit to industries such as pharmaceutical, medical, finance, telecoms, they also will bring the opportunity for nefarious actors to steal data. And the way they'll do that is by breaking today's encryption that we use for digital telecoms. So that's the big concern, and that's why we're introducing post-quantum cryptography. Now, for those old enough to remember, and there might be a couple in the audience, Y2K was, the last big kind of audit that we needed to perform to ensure that our systems would get past a certain date. Now, I was involved in this. I worked with a company called Ericsson in Dublin, and we had a Y2K project team. And that was, our job was to go through all of the software and look for any 2-digit dates and change them to 4-digit dates, because the worry was when the clock ticked over from 99 to 2000, those digits would go to 00, and that was considered a potential reset code in software. So that was the big issue and the big concern for Y2K. Now, there's a lot of comparisons between Y2K and Q-Day, Q-Day being the date at which quantum computers will be able to break today's encryption. So we don't know when that date is coming, but it is coming. And if we compare the two projects, Y2K and Q-Day, you'll see a lot of similarities. So, there was a big project needed to audit code, to audit systems, and to make a replacement of some kind or other. There was potentially huge impacts as well. So for Y2K, there was concerns that planes would drop out of the sky, that ATM machines wouldn't work. So there was a massive amount of impact if we didn't get this right. Now, luckily, looking back at Y2K, it kind of went okay. There was very few issues, but the cost I read recently was $300 billion US dollars globally to get Y2K in place and get us past that line. So Q-Day is going to be somewhat similar in scale because there's a huge amount of verticals affected. There's a huge amount of processes that need to be audited. And then all those current encryption algorithms need to be migrated to post-quantum encryption algorithms. The only problem is we don't know when Q-Day is coming. So it's been kicked off now, this migration activity. So you'll see roadmaps, you'll see migration plans being kicked off, especially by the verticals like finance and government and military. They're the ones who are really concerned that their data is going to get harvested now and maybe decrypted later when we get quantum. So that's kind of setting the background. So what's the big difference between today's encryption keys and the ones that are being developed for post-quantum? And it's really key size. That's what it is. This is a very simple diagram to show you that today's keys are a certain length, number of bits, and the ones that are being developed for post-quantum are just longer keys, more bits, which makes them more difficult to be hacked by quantum computing. But the problem is the PQC algorithms, they will have an impact on CPU consumption, memory, latency, and other end-to-end performance metrics. So that's why there is a concern. And that's where testing needs to come into play. So why do we need to performance test PQC? Well, part of my job is to look at industry and what's happening across the different verticals. And, whenever there's a white paper or a report or a migration roadmap to do with PQC, I download it, I read it, and I make sure I understand what's in there. Now, on screen are 12 such reports that I've recently looked at. And, they kind of cover a wide spectrum of verticals. There's government in here, there's telecoms, there's finance, there's military. So, they're all saying the same thing, by the way. They're all saying that we need to migrate to post-quantum. We need to start the migration now. But also, if you look at these reports, there is nearly always a section or paragraph or a full page on performance impact. And I'm going to give you a couple of examples from here. So this one it's a UK quantum strategy for sovereignty and scale. And in this report, they say, not all quantum safe algorithms will be suitable for every application. Trade-offs in speed, key size, and the complexity of implementation means that different systems will require different solutions. It also says that without visibility, government and regular stress testing, migration efforts will lag, leaving essential services exposed. So kind of a point towards stress testing there. Another one, this is from the GSMA. Now, GSMA are the body who look after all mobile operators worldwide. And they've written a document called Migration to Post-Quantum. And in it, they say that deployments must enter a testing phase to assess the viability of certain post-quantum cryptographic algorithms to minimize performance. So again, talking about testing, the reason being to minimize performance. Similarly, from Japan, the operator SoftBank have said that when cryptographic protocols are deployed, they can place a significant load on telecommunications, causing latency, resulting in poor quality and lower throughput. And then lastly, this is from a Dutch company called PCSI, who are looking after enterprises, small, medium, and large. And they said that, IT departments would really benefit from real world experiences like benchmarks conducted in real world implementation scenarios. The reason being that when IT companies need to upgrade their VPNs to PQC safe VPNs, they want to make sure that there's going to be no impact on the end users or the employees who dial in over VPN. But the one I like most from all of these reports is this one from the financial world, and it's from a company called BIS, which stands for the Bank of International Settlements. So what they did was they look after all the central banks of Europe. So they basically make sure that all financial transactions between central banks work, but will continue to work. So 2.5 years ago, they wrote this document called Quantum Proofing the Financial Industry. And they looked at doing some testing where they wanted to see if they upgraded to post-quantum algorithms, what would be the impact on financial transactions. And now the reason I really like this one is because they showed the tests that they performed. And these are the 8 tests that they said they would conduct. And these are perfect. These are what we would have recommended had they come to us if they asked for advice when it comes to performance testing. So you can see they've said that they want to set up a VPN, secure tunnel, using post-quantum protocols. They want to compare the comparison between traditional, which is today's algorithm, with the post-quantum algorithm. Then they want to look at the difference between different post-quantum algorithms. Then they want to set one up from scratch, et cetera, et cetera. So these are really strong test cases. What they didn't do was they missed scale test. So they just did one transaction, one financial transaction between 2 central banks, and they checked how it worked, and it worked fine. But they didn't do a scale test, which is really important when it comes to finance, especially. They didn't do impairments. They didn't put in errors to see, well, what would happen in the case that there might be impairments in the network. They didn't do key rotation. They didn't do key generation testing. And they also missed repeatability. So because this was done on a live network, if they did that same test an hour later, the conditions change because it's a live network using routers, using different routes. Whereas if you do this in a lab, You've got controllability. You can repeat that test again and again and again, knowing the conditions are all the same. So I reached out to the author of this white paper, and I just gave my feedback, and I never got a response, but at least I was able to give them my thoughts. And then last month, they introduced the second iteration of this project called Project Leap 2. Now, for this one, they actually did high volume test, and they put in a negative test scenario, which is really good. They were the two of the points I brought up. But if you look at the bold text here, they said that in this second project, the tests revealed significant performance differences between traditional and post-quantum, pointing to the need for further testing and preparation before transitioning. So there's a worry here now that, 1 month ago, this big financial institution have said that we did a bit of scale testing and we found some really worrying signs. And they said we really need to do more testing. So scale test impairment was added, but if you look at the actual results, this is from their paper. It shows that the tests all passed, but that there was significant differences between traditional and post-quantum, insofar as the post-quantum signatures took 209 milliseconds to establish compared to the traditional, which was only 28 milliseconds. Now that's a huge difference when you look at the scale that's happening there. So, from our point of view, we're a test company and we would recommend testing, but it's nice to see that the actual industry itself is talking about the need for performance testing. So the reasons we think testing should be done: one size doesn't fit all. So, edge devices, they will be limited compute power and they will have smaller battery sizes. So they will need to have a suitable post-quantum cryptographic algorithm to maintain their performance. Scale test is really important. Single instance tests doesn't present the full picture, so you need to test in accordance with the use case. You also need to understand the limitations because, we're not testing to prove something doesn't work. We're testing to show the deficiencies where there is fault, where there is failure, and then you can mitigate against that. So understanding the bottlenecks, understanding the CPU limitations are really important. And the last one here is also important: cryptographic agility. So this is the ability for an organization to be able to swap out an algorithm if it's breached. So let's say NIST, which is the National Institute for Standards in the US, who are proposing the next layer of algorithms. If they say that one of the algorithms they've proposed has been compromised by quantum, then you need to take another one off the shelf and swap that into the network. But the one on the shelf, how do you know that's going to be fit for use? You need to have done continuous testing to make sure that that will always work when it's dropped in at short notice. That's what cryptographic agility means. So we've done some testing. These are the results that we found. Now, the good news is that, migration to PQC for TLS and IPsec is achievable, but with proper planning. We also noticed that you do need an uplift in hardware, in architecture, in the underlying architecture, because there is an infrastructure capacity increase between 50 and 75%. We also noted that comprehensive scale testing is non-negotiable. You must do scale test if you want to test the limits, so you will always be able to have the worst case scenario covered. And there is a clear return on interest return on investment if you do proper testing. Because if you leave the testing and you just go straight out into the industry, into the live network with new algorithms, and you face failure, then you're going to have unhappy clients, you're going to have potential bad press, you're going to have financial penalties, and then you're going to have to do the testing anyway. So it makes huge sense to do this testing up front, and then you launch with confidence. So because I've only got 1 minute left, I can share some of these results later, but we saw all these down arrows shows the performance with the PQC algorithm compared to traditional. So, you're seeing an average of 30 to 40% decrease in performance, whether that's connection setups or whether that's time to first byte. You can see a massive reduction in performance because the handshake required for these new algorithms takes so long. So these results we can share offline. But because we're stuck for time, the the kind of last slide I want to show you here is that all of this can be mitigated against. So, we recommend performance testing, we recommend benchmarking so that you understand where the bottlenecks are, what the issues are. And then you can start taking remedial issues or actions such as optimizing cryptographic operations, maybe using different algorithms for different use cases. You can also introduce hardware acceleration so you can boost the CPU capacity and capability. Or you can do some kind of network and protocol tuning so that maybe you can, trust in certain circumstances, trust the first handshake and not have to do a repeat handshake along the chain. So to finish up, Q Day is coming, and with the proper planning and preparation, we can get past Q Day as we did with Y2K and keep our data intact. Okay, that was it for me. Thank you very much.
You have 5 questions, because I don't expect the panel to take full hour, so yeah.
Okay, so thank you for the presentation. I have several questions. One is, you test the hybrid solution? Because now we are talking about that we don't fully trust even the post-quantum PQC, let's put it this way, that they are not tested time-wise. Did you test any of the hybrid solution?
You mean QKD?
No. Standard like RC plus lattice space.
Oh yes, we did. So do you know, Damien, the colleagues in the audience?
And what we see is when we look across the security levels, so we look at information, this is the level of by level of sets the same for the next tool with that attach, incorporating the hybrid algorithms. First, you're seeing across the security levels super very interesting on the algorithm. So you're getting the same performance at level 1 that you're getting at level 5, where you compare that passport or say as the difference as but then when you incorporate the same test, then it gets
Thanks a lot. So the second question is because we know that European Commission not some programs to say the integration of PQC and parallel protocol, because we are only talking about the security algorithms or security protocols, but there are many applications. The security protocols will be embedded into hardware applications. I think really, if we increase time or size of subtext or signatures, this would significantly affect the application. So what's your opinion on that? Because that's very important for the adoption of the PQC.
Totally agree. And so, our view is that you need to test that. You need to test it in a lab, but you need to test it with real applications, real traffic. And, our tool is a emulation tool. So we emulate users, we emulate traffic, and we emulate applications so that, you get a very good impression of what's happening in the real world before you deploy in the real world. But you're right, when you start scaling up and in the higher levels, then you need to understand what's the actual impact. So it's very important that you do this testing, but you also then are benchmarking with the correct metrics. So, you're able to see what is the impact. If it's latency, is it throughput? Is it connections per second establishment? Is it MOS score? So all of those metrics are really important. and especially for the different verticals involved. And you're going to have more important metrics depending on the different vertical, but that's where we can, you know, absolutely test and recommend testing. You're very welcome. Any other questions? You done? Yeah.
Thank you, buddy. I just want to let you know, hear your thought on very low power devices.
Yeah.
Because they will be the part of the ecosystem, and we see like, you know, quantum computing is happening. So how do you see, like, you know, the security for those low power devices? I'm not talking about edge device, but more free flow.
Yeah. Again, so what NIST have already recommended, they recommended certain algorithms that they've tested, and they've said that from a security point of view, these are robust. And actually, you know, the point is that even though they can say they're robust now, we won't know until quantum computers are actually available. And maybe they won't be as robust as they hope, but the plan is they're robust. So, you know, we do have a small number of already recommended NIST algorithms, but they're not always going to be suitable for the small devices, which are low compute and low powered. But there is a huge list of just not recommended PQC algorithms to date, but we already support all of those non-recommended ones. It doesn't mean they're not suitable. It just means they haven't been recommended by NIST. But there is a big interest in those non-recommended PQC algorithms because some of them will be more suitable to the smaller devices, the low power devices, the less compute power devices. And that's why we're getting interest from our customers to look into testing those particular algorithms, because they're more suitable to their use case. And also, you know, they might be the ones that aren't immediately targeted by the nefarious actors once the quantum compute comes out, because, you know, if you have one that's off the radar, then it might be more safer to go with that one. And also you've got establishments who kind of go across different countries, and there might be individual governmental recommendations or regulations on one specific algorithm, but that mightn't suit, for example, NATO, who have, you know, a wide ranging number of countries that they need to support and adopt. So they may also need to go off grid and look for their own algorithm. So yeah, you need to then start looking into the non-PQC recommended but applicable algorithms.
Thank you.
Okay.
Thank you. Well,
Thank you.
were we clapping?
I think I got one.
Oh, you got one. I've got another one for questions and answers. Now we'll have last presentation now before we begin with the panel. So we